I'm Mark Gustafson. I work on our OpenConnect CDN, and again, I'll explain what all that is. This is Asher Feldman, who actually did most of the work, and he'll be getting into the guts of what did we have to do to make Spinnaker deal with something that is definitely not a cloud provider. So first, we will run through, I'll give those of you in the audience an introduction. I won't introduce Netflix. I'm hoping everyone understands what Netflix is, what we do as a service. If you don't know that, then talk to half the people here and we can explain what Netflix is. But I don't expect people to necessarily know what OpenConnect is. So we'll run through that. We will run through what we mean by our firmware deployment model and why we felt any need to change it whatsoever. Then I'll do a little bit of history about where we came from and again, why our use case is so very different from most cloud instance continuous deployment models, and then how we did end up changing it and how we are using Spinnaker in production today. And then again, I'll turn it over to Asher, who will get into some of the gory details for those of you who are really into Spinnaker dev/configuration. So again, just as an introduction, so Netflix, again, we serve movies. We delight our customers with movies and TV shows. We stream video over the internet. Up in the left, you'll see that is your kind of Netflix device. And then down here is where everyone generally at this conference is pretty familiar with the idea of Netflix and the idea of running Netflix within AWS. And that is true for the vast majority, a lot of interactions that the client has with our set of microservices. They're all in what I'm calling here the control plane, or what we call the control plane. What people may or may not understand about our service, though, is we do differentiate, and we do have this upper layer, the data plane, which includes a content delivery network that we call OpenConnect. So again, just to make it even more obvious how this breaks down, is everything up to the point before you start streaming, when you're interacting with the app, you're browsing for movies, you've logged in, etc., all those interactions are with AWS. But once you hit play, and the client actually goes back to AWS and gets a little bit of steering information, then it's going to start making requests directly to the data plane, to OpenConnect. So again, a little bit more about, OpenConnect. OpenConnect is a Netflix original service that is a content delivery network, purpose-built for delivering our content to users at incredible efficiency and incredible scale. What is a content delivery network? Again, just in case you don't know. The idea is you take lots and lots of caching servers, you place them all around the globe, as many places as you're trying to get close to your end customers. For Netflix, our customers are basically everywhere in the world, with some very, very minor exceptions. And so we are trying to get geographically distributed, and inherent in the idea of a CDN is that you also have some amount of logic about how you actually direct client requests to the right cache. And in OpenConnect, again, we are very purpose-built for our application where we know that customers are looking for a particular set of content. So again, we have the concept of steering customers directly to the best cache that we know already has the content they're looking for. So a little bit of history, again, about how this kind of has evolved, and again, what the OpenConnect infrastructure looks like relative to, again, other cloud services, other microservices, or even other CDNs. Is we started back in about 2007 doing streaming over the internet using a platform called eHub that honestly I can't tell you very much about because I wasn't there, and almost not too many people I know actually worked on it that are still around. And then we moved into a period of time, several years, where we did start to work with some of the largest content delivery networks in the world that are, again, multi-tenant server groups, and we used multi-CDN in order to make sure that we weren't, we didn't even have a single point of failure on any of the even major services, et cetera. And the service was growing, during these years. And we could see pretty early on, or as we went up that growth ramp, that eventually our scale of doing video over the internet was going to be more than was going to be comfortably provided, even by the largest CDNs, or even all of the largest CDNs. We're going to have trouble handling the scale that we knew we could grow to. And in fact, that has been the case. We've seen the growth since we brought OpenConnect. So we luckily did a great job of making the decision and designing a brand new purpose-built CDN from the ground up, again, starting in about 2011. So that is what OpenConnect is. Now, part of, again, what goes into building your own CDN is, in our case, we also design our own hardware. This is, again, purpose-built for our use cases, where we kind of segregate two general classes of what we call OCAs, or Open Connect Appliances. I'm sorry, I kind of skipped it over there, but that is the OCA. Actual caching appliances. This is an example of a storage appliance, which again, we have two basic models, storage, and I'll get to the next one in a moment. But basically, this is for all of your content, including all your tail content, which again, we shard the content across multiple boxes, so it's not like every single box has the entire regional catalog, but a set or stack of boxes in a given region will hold the entire catalog, and so any given request will find some place that you can serve it from within that stack. Then we also have flash or offload appliances, OCAs. And again, the whole notion here is, well, these are all flash drives, very high I/O. We can get, again, we've published this publicly, that we can get close to 100 gigs off a single box. Again, we've got lots of copies of the most popular content, and our steering logic knows to basically put these boxes in front of the vast bulk of those requests that are coming in for really, really popular content. For those that, again, are not so popular, it shouldn't even be found on a flash drive, so the request would never even go there. Instead, that would get shuttled back to a storage server. So this combination of basically flash OCA and storage OCAs for head content and the broad tail, that basically makes up our physical infrastructure for actually serving it. And we'll talk a little bit about how we kind of need to manage those or not. But first, I'll also talk about the design of the content delivery network itself. Besides designing our own hardware, the other thing that we really wanted to do that's pretty fundamental to the design of OpenConnect is we wanted it to be as distributed and well connected as possible. So I will get into exactly what that does look like, but that number, even 95% of our traffic is directly connected, that's a safe number, meaning it's, if anything, it's probably even a couple percentage points closer to 100%. We're not quite 100% directly connected to all of our end user customers' networks, but we are very, very close. And that's very, very deliberate. And again, we'll get into exactly why that's important and how that manifests itself in both the network design and also how we actually manage deployments, because it does have important implications. So again, one way that we achieve that is we make it really, really low friction for all of the end user ISPs to basically get OpenConnect appliances in their edge networks. Again, basically directly connected to the users. We can give them appliances, we provide it, it becomes their hardware. They have to provide space and power to keep it online, and we manage it for them. We will directly connect to it and again, monitor and manage and handle firmware upgrades, but basically it's their server in their location. And in addition to that, we also provide very, very dense connectivity. So that's kind of this, what I'll call the sparse connectivity at the edge. We also provide very dense connectivity at internet exchange locations throughout the world. And if you're not familiar with what an internet exchange location is, here's an example. So you probably can't, unless you're really, really into networking, you probably couldn't tell what building that happens to be. It's just a nondescript gray building. If you knew it, it is the London Internet Exchange. If you went inside, you'd see lots of this stuff. Basically, a lot like any other data center with rows and rows and rows of caged servers. But what's unusual about an internet exchange point is they're specifically there to connect to each other. It's not just colo for a large AWS or Google or Azure build out. It's specifically places where networks can come together and basically have ports in close proximity and directly connect the networks. And there's, again, a number of these around the world. We'll see a little picture in a little bit. So here's an example of an implementation inside of an IX, where off to the left you actually see some networking equipment. Again, just a pair there mostly for redundancy. And we see a couple of stacks, again, stacks of flash servers and stacks of storage servers. And this is an example of a fairly typical size, and again, IX locations where we are connecting directly to hundreds of other networks in a single location can very well have hundreds of servers, hundreds of OCAs in a single site. So again, just to make it even more obvious, so if we have our end users over here, one of the ways that they can be most readily directly connected to us is they're going upstream immediately to their ISP who has an OCA on premise in their data center, basically as close as anything else on the internet can be. And they, when they're streaming their content, they're getting it directly from there. We do always, for the sake of resiliency, want to make sure that every client has more than one spot they can go to retrieve content. So even if that OCA does go down, and if there were only one OCA in a site, which is possible, and if the OCA needed to be rebooted, and we'll get to that in a moment, then there is upstream connectivity. So a user over here, again, if we take a hypothetical example of a family of 4 who wants to start streaming a new hour-long movie every 15 minutes on 4 different devices, if I actually took that OCA down, they might not even notice that anything happened, right? They'll simply fetch from someplace upstream, and again, as long as that upstream connectivity is decent enough bandwidth, they won't notice that they're actually streaming from the IX. In this case, again, if that OCA went out of the picture, or maybe it was never there in the first place, again, there are some ISPs that only directly connect to us in the IX and don't necessarily have local OCAs, the user doesn't necessarily know. Now, the ISP probably definitely does know, and we'll talk about that, where again, especially in those cases where you have an OCA on site at an ISP, they care very deeply about maintaining that traffic locally. That helps their fixed costs get amortized over a certain amount of traffic. They don't have to pay marginal costs or deal with, again, a potentially scarce resource in terms of their upstream bandwidth all the way back to the IX. So here's a latest snapshot of, again, our global deployments around the world. You can kind of see there's slightly larger orange dots. Those are IX locations. All the green dots of various sizes are individual ISP locations. Don't try counting them. I'll give you a hint. There's thousands. Several thousands of individual sites. Again, in every site there's at least one box, sometimes only one box, sometimes hundreds. So we have many thousands of OCAs around the world. And we do our best to try to think of managing them as a fleet. Again, if we go back to the paradigm about how you manage your servers, herds versus pets, we'd like to think of them as herds. But the downside is, again, when you're one ISP in a remote area of Brazil, which there are a number, and maybe you don't have enough traffic to really justify more than one OCA, then that OCA is a pet. And you care very deeply about every minute of uptime on that OCA. So that now gets us into, well, we've been managing firmware updates on these OCAs for as long as we've had the Open Connect service. We periodically have to modify the software, and by firmware, again, it's a little bit different. It doesn't just mean chip firmware, although it can go down to the level of possibly updating the image on a NIC controller, on a hard disk controller, right? As well as the base OS, which is FreeBSD in our case, as well as any application stack, which is basically Nginx for the main web server, and a variety of other, again, pretty fixed images of software that we run, all of our proprietary tooling and everything on the box is what we call the firmware. So this is a bare metal base OS and application image that gets applied to the box when we need to change it. So we've been doing this, again, for as long as we've had Open Connect. We've had to be able to manage these boxes out in the field, update them periodically. And so we've built a number of tools over the years, primarily using Python scripts, primarily operating against, again, kind of a core tool set that here, internally we call it just CDN admin. This is a set of APIs and things that were built to manage the state and keep track of the state of every cache in our system. Now, as we've grown over the years, this has become more complex. We'll talk a little bit about some of the variants that we've had to account for and just other complexity that comes into play as we get just more and more OCAs out in the field, and just other aspects of that back-end data system that really held CD and admin together, that we felt it really did need to become, it needed to get refactored. So as we were looking at making that change, now, basically just about a year ago, we basically were looking at, okay, if we're gonna have to do this refactoring, what other types of things should we even consider in terms of how we do it? Do we just rewrite everything from scratch on a new set of APIs and change nothing else? Or do we take a bigger step and actually move on to what we could consider to be a stronger foundation? And that's exactly where Spinnaker comes in, and that's exactly how we end up at this conference. Is Spinnaker, within the last couple of years, and especially within the last year, has absolutely become kind of the paved path within Netflix, a lot of support, a lot of momentum, and it just, again, gets used for all kinds of workloads. Now, not for our workload, and again, our workload is very, very different, and again, Ash will go into, again, some of those nitty-gritty details, but I think you can, again, kind of see how, managing a number of hundreds of potentially distinct, unique OCAs out in these very sparsely populated edge locations is a bit different than how you generally manage your cloud instances or instances of a microservice. So I'll go into a little bit about how we did used to handle it. Well, okay, I already shared it's Python scripts developed and maintained within our relatively small CD and ops team. Basically all about command line driven stuff within a bash shell. It, again, was fairly manual in terms of, again, as an operator, you run the scripts, you'll see in a moment you'll get a certain amount of output, effectively console output that you can look at. It's also all being logged. So if you do need to go back and look at something, you can go check through the log, grep it or tail it. But I can tell you that trying to actually look at, well, what's the overall status of my deployment? Because again, if we now take a step back and think about deployments do take a number of days. We do them in batches, we do them in sets. We start with small, potentially pilot sets, make sure that everything is looking good. And then by the time we actually get out to those ISPs that have a single box, we want to know, again, that it's already been proven in the IX locations. It is a little easier for us to recover in IX locations where we have a little bit more kind of hands-on, remote smart hands without having to go and actually involve the technicians from the ISPs, things of that nature. So it's, again, a very progressive rollout with a lot of quality checks as we go through it, and really seeing that status, knowing exactly how many have failed. And again, across many thousands of servers, every time that we do roll this out, there'll be some failures, whether it's just an issue with the boot disk on the box, or something else went wrong, or quite frankly, maybe the ISP had a network carrier issue and they weren't able to download the firmware properly the first time, etc. A number of things can go wrong, and if you do something enough thousands of times, it will go wrong. It may or may not be recoverable. Again, sometimes boxes actually go bad and we actually have to submit them to get returned back to us. We have some boxes out there 6 years old. They aren't going to last forever. Just as another example of, again, kind of what we would be looking at, and again, don't try to read it. It's just console bash shell output. But the highlight is that basically we would run these custom scripts that would give us a couple of different panes of information. One would be about the actual upgrade engine kind of background, and then the lower part is basically all about the scheduling, and again, what has happened. So depending on exactly how large of a batch you may have addressed within the last n number of minutes, you might see the last 10 minutes, maybe up to an hour of the most recent information. To go any farther back than that, again, you're looking through log files. And again, we would have the ability to also set things up to schedule them, so you could, again, set up roughly 4 days or even a week's worth of activities that then would actually continue to run. So you could disconnect from this, reconnect, but basically a long-running script is basically what our past deployment method was. And again, in terms of how we had to interact with this as operators, we did have a number of, again, manual checks that we would go through before we would start. We do go through the process every time of sharding the OCAs, because again, we have this fairly significant resiliency rules. So again, if you have a small site, you don't want to take all the boxes down at once, right? Pretty obvious. We have sometimes specialized roles. Again, I won't really go into them. I refer to them there as boxes at our fill site, boxes with special versions of our firmware that are called no delete. Again, I won't dig into all those, but just take my word for it that they are variants that have to be handled specially. So we would learn how to do that or trigger them separately. The other thing that's interesting is, again, notifications to ISP partners, because again, these ISPs care deeply about every single box in their infrastructure and how well they can keep that traffic local. So they want a lot of notification. Also, some of these ISPs are very large ISPs, your kind of incumbent nationalized telcos that are very, very process driven. And so the idea that you're going to have maintenance without telling them about it days in advance and having it line up with their maintenance window, it's not going to fly. So you give them an advance. You tell them exactly when it's going to happen. You make sure it stays in advance. They give you a ticket back and blah, blah, blah. And the point is that all of our scripts would have already handled that. And then again, checking the status and again, responding to issues, because there are going to be failures. So we would have automatic ticket generation. We would be able to track through and follow up with every single OCA that did manage to not come back successfully or not get upgraded successfully. And then we would have a post-upgrade checklist. So how's that different now that we can actually use Spinnaker? And again, Asher will go into all the details about how we translated those same sets of requirements over, but basically we did map, and so far we have mostly just replicated the same overall process, but I'll also give you a preview that part of the reason why we did it is that we think that as we move forward in the future and we actually kind of think out of the box about how to manage these deployments, it'll be much easier to iterate and much easier to change within Spinnaker than having to go back and again just rewrite things in Python. So in short, we still have a sharding step where we have a pipeline that goes through and again applies these very specific resiliency rules about exactly how many and which sets of OCAs can be operated on at a given point in time. And then once we're actually ready to deploy the firmware, we have a deployment pipeline that again takes in, and the main point here of these is not to look at what all the parameters are, but just there's a few parameters that do specify, we name the batches, we can specify start times so that, again, it's going to take place only during trough hours in local time. Again, and Asher will talk about how that becomes interesting complexity because, again, we deal with every single time zone in the world. We do specify a particular firmware version. We also attach tickets to it. You can apply additional scoping. And then basically you're ready to push the button and run. And then as it goes through, it basically turns in all the various stages. And again, if you guys are familiar with Spinnaker, I think most of you are, it's fairly standard UI, basically telling you what it is operating on or what's coming up next within the prepared upgrade plan. So that's the overview, or most of the overviews. Asher will go into the deep details. I do want to back up and note. So what all again, is involved in this effort? How much dev time did it take? Well, it was only about a year ago that basically Dayton and Andy Glover even talked about, my boss is Dayton, by the way, he's sitting over there, talked about us even wanting to do this. We gathered requirements again in Q4 last year. Basically, it was Q1 of this year for basically one dev, and that's basically Asher, who did most of the work. We have been doing a certain amount of slow rollout since then, and we had some dependencies over the summer in terms of, again, new API endpoints that we actually needed as dependencies that weren't necessarily ready yet. So that's the only reason why we're basically not ready to basically say we're at total feature parity and we're basically ready to go into maintenance mode or minor feature updates. So we do still have some things where but we are now able to use it for all of our batches. We've, again, been running it in production for the fleet for several months now. And again, it's been great. And with that, I'll actually hand it over to Asher to talk about how we did it.
Thank you, Mark. And yeah, regarding that timeline, everything I'm about to cover took about 8 weeks of development time, spread out over a quarter with plenty of interruptions, with some perhaps 4 weeks or so of follow-up work in the subsequent quarter, just adding some UI polish and additional features. So initial concerns when approaching this problem set for the first time as well. If you look at the history of Spinnaker, it's really developed around Netflix's cloud delivery needs and cloud delivery patterns. So we've got deployment strategies like red-black, immutable infrastructure, clusters of applications contain ephemeral server groups made up of even more ephemeral instances. If something goes wrong with a software deploy, it's not really a big deal. You can always roll forward or quickly roll back if you deployed with a red-black. If a bad application build goes out and you have maybe broken server groups left over, that doesn't really matter either. You can roll forward, and eventually they're just automatically going to get cleaned up. Unfortunately, if OCAs were left out of service due to a failed deployment for any reason, that could impact streaming availability, or perhaps more importantly, given the large amount of redundancy and capacity in the OpenConnect fleet, it could impact customers of individual ISPs. So if an ISP is serving 35% of its network traffic to Netflix streaming customers on their network, and suddenly that bandwidth was going outside of their network, that could impact all of their customers, whether or not they happen to be streaming Netflix. Operations must be idempotent and resilient. Idempotent infrastructure operations are just far easier to handle failure cases for. So I'm bringing this up specifically because, at least with the AWS cloud provider, there are many things within Spinnaker that are not currently idempotent, things like create server group. There are cases where we would actually fail a deployment pipeline because something went wrong with the cloud provider that we don't necessarily know what the end state is going to be, so we just give up. We want to avoid that as much as possible here. I think we'll get there with the public cloud providers as well. And then one of the initial debates was, should we treat the OpenConnect fleet as a cloud provider? So it's this huge global footprint of powerful servers. We have an in-house configuration management system for them that happens to provide a very nice, well-documented, strongly typed API. During the deployment process, we do need to cache the state of individual OCAs, which is similar to things CloudDriver does in caching cloud provider state. However, if you happen to attend Rob Fletcher's talk yesterday on Orca, he talked a little bit about the journey Orca went into becoming a truly resilient distributed system that can horizontally scale work and which has a durable queue, so that if a instance working on a task fails, that task is going to just fail over to another instance. CloudDriver is not quite there yet. Currently, tasks are bound to a specific CloudDriver instance. If that instance fails, that unit of work is lost. So it kind of broke with our own internal conventions, and everything we're going to talk about was implemented purely in Orca. So some logistical challenges in ways that OpenConnect deployments really differ from our typical cloud deployments. So OCA maintenance occurs at trough, mostly around being kind to smaller ISPs, where they may not actually have enough excess capacity to have all of their Netflix traffic suddenly transit outside of their network. And as you saw from the global map, we're in practically every time zone. There's actually 38 time zones around the world today due to some countries having 30 and 45-minute offsets. So we've already have a deployment window feature within Spinnaker, which would commonly be set once per pipeline. In thinking about this, we had to think about, okay, how can we have up to 38 different deployment windows for what would essentially be a single deployment stage? And as mentioned, we need to honor site-specific redundancy models. There are some large OpenConnect sites where we could just randomly pick a quarter of the hosts to take down to upgrade, and nothing could possibly go wrong. There are other sites where if you randomly picked a quarter of the hosts, you might take down the entire site in doing so. So we can't leave that to chance. So the first stage that was implemented within Orca around this was a sharding stage. Basically gets all of the OCA metadata from the configuration management system and builds shard keys that basically account for the key resiliency aspects in order of operation. So the type of content they include, whether or not they announce BGP routes, and which set of BGP routes they're announcing, if so. Basically stuff that into a sorted red-black tree as a map of key to cache IDs, cyclically assign them to shards, and since we've clustered together like caches with the same responsibilities, that just guarantees that all of the OCAs at this Amsterdam site announcing this particular set of routes are going to end up in different shards. So the deployment process itself, the first stage relevant there is really just a specialized scheduling stage. It takes the parameters that Mark showed earlier, and those parameters really define the desired end state. I want OCAs in this shard or a subset of those OCAs to run a specific firmware version. This stage basically just outputs a map of times to OCA lists. This didn't necessarily need to be built as a standalone stage, but my first reasoning was paranoia. This is an absolutely critical system to Netflix, and I wanted to ensure that operators had the opportunity to review that upgrade plan before it was acted on. I would not want a Spinnaker bug to result in all West Coast OCAs going offline at the same time. I think we're a little bit past the need for that, but having this as a dedicated stage also allows us to generate future plans consumed by other tasks. So in this case, we have a need to inform ISPs of maintenance several days in advance, and we can produce a plan that meets that need as well as the actual deployment need. So if you looked at the pipeline view for one of these firmware pipelines, it's really simple. That prepare upgrade plan, this is the scheduler, optional manual judgment, and there's two parallel stages, schedule upgrades and upgrade engines. Depending on the scope of a deployment, though, these actually turn into between 5 and 83 parallel stages. So the stage graph looks something like this, although larger. The dotted lines represent the actual stages in the graph when building a pipeline. The solid lines are synthetically injected stages. So we end up with a start upgrade stage per unique start time, and this thing called the upgrade engine, which was really just named that way to carry over terminology from the previous Open Connect deployment processes, which spins up a bunch of purpose-built stages, each one responsible for a individual part of the state change along the deployment process. So the start upgrade stages, they operate on a predetermined set of OCAs at a predetermined set of times. And their main responsibility is to put OCAs, when they enter their local time zone trough, into a state of traffic draining. So basically, the Netflix control plane will stop steering new streams to those OCAs. However, they will continue serving any existing streams. The upgrade engine stages are completely orthogonal to that schedule. They do not operate on a predetermined set of OCAs or a schedule, and this design was really important to making this process as reliable as possible. So just a little code snippet. This is an example of how we take a schedule, which is a map of times to caches, and turn that into a bunch of stages added to the graph with start time and list of caches involved. So what did those upgraded engine stages do? Look at the monitor draining stage. It's basically just continually. Yeah.
How long does it take for an OCA to drain traffic?
We
Short answer is it depends, but basically less than 2 hours. Because basically it's going to last no longer than your longest singles.
Yeah.
And it won't even wait till the very last one. Again, there's a bandwidth threshold, so after you're less than, say, 100 megabits or so, then we'll consider you drained.
Which is tunable as well. So, yeah, we might have some titles that are 3 hours, 3.5, but not much beyond that. So this is just continually searching for OCAs that meet that original deployment scope that have started the draining process. It keeps track of when they're first seen so that we can time out and fail an OCA if for some reason it's still pushing too much traffic after the timeout window, which is typically 4 hours. This stage integrates with our the Netflix telemetry system Atlas, and it is continually querying Atlas for bandwidth metrics about all of the OCAs it is currently concerned with. If an OCA fails to reach reach below the bandwidth threshold within the 4-hour timeout window, it marks it as failed, and which we'll handle later in a different stage. If it drops below the bandwidth threshold within the allotted time, it initiates the actual firmware upgrade process, which causes the OCA to pull down the desired firmware version, apply it to a boot partition, we set some other special flags, and then it will reboot into the new firmware release. The monitor upgrade stage is similar to how monitor draining is continually just scanning for OCAs that meet its condition. It's looking for OCAs in the deployment scope that have been told to upgrade to the new firmware, but have last reported in as running on a different firmware release. We also track the time. I think we give OCAs 2 hours to successfully boot into the new firmware version. If that doesn't happen, they're again marked as failed. If it does happen, once it sees an OCA that it was previously tracking that is now reported as up and running on the new firmware, it's still going to be out of service at that time. The monitor upgrading stage is responsible for transitioning it back to its prior state. When caches have been marked as failed, we have a dedicated stage to handle that, since there's some additional business logic in there. We set them into a special state called wonky, which allows Open Connect operators to quickly identify any OCAs that fell into this vortex, and any OCA in that state is out of service to our steering control plane. We'll open a individual JIRA ticket for every failed OCA, which gets assigned to whoever lucky person started the pipeline. If that OCA belongs to an ISP versus a Netflix Internet Exchange, we will notify that ISP that that particular cache is left out of service, and a Netflix engineer will follow up with them during business hours. We've also got a fairly important stage, monitor deployment. On the one hand, it's collating metrics across all of these parallel stages to feed the UI. Perhaps more importantly, it implements a circuit breaker. So if more than a tunable percentage or absolute value of OCAs fall into the failed state, there might be something wrong, possibly with the firmware release, possibly something else, but we might want to shut things down early. It actually sets a flag within the execution context that all of the other stages are continually checking. So if there are still start upgrade stages out there that have yet to start OCAs down the path of draining traffic, those stages just become no-ops. If the monitor draining stage is watching a set of OCAs that are draining traffic, it will actually just revert them back to their prior state, so put them back into service. Once OCAs have started the process of rebooting into the new firmware, those are kind of past the point of no return. So the monitor upgrading stage doesn't do anything different. But this stage, once the circuit breaker has been set, we'll wait and we'll just continually watch for the state being reached where there are no OCAs that are actively draining or upgrading, or where there are no OCAs marked as failed that have not been handled. And once that condition is reached, it will terminate the pipeline with a status of canceled. So these upgrade engine stages, they work asynchronously. They don't share state across the stages. If Spinnaker was to go down for any reason, which definitely never happens, we definitely might be left with hundreds of OCAs out of service. What do? You really just have to rerun the pipeline with the same deployment scope. Those out-of-service OCAs are not going to appear in the new deployment schedule, but the upgrade engine stages will pick them up and will still get them to the desired state without really any thinking about cleanup specifically. So, result, reliable, repeatable delivery to stateful, mission-critical physical infrastructure, which is Mark's description for the talk. So everything I just described is closed source, primarily because it's a deep integration into existing closed source Netflix services and infrastructure. But I think this is a great example of how extensible Spinnaker is, especially Orca. So if your business has complex workflow automation needs that don't correlate to cloud deployment primitives or Spinnaker's existing functionality, don't let you scare that off. It can be expanded to handle just about anything. And thanks to people across many teams who helped make that happen. And I think we might be out of time, but happy to answer any questions.